Okay. Hello, my name is Nathan, and today we're going to be talking about overcoming an untrusted computing base, detecting and removing malicious hardware automatically. Here's introduction. And the agenda for today, the first thing we'll be talking about is the background and the motivation for this project, why they had something like this made and why we needed something like this made. And then we're going to be talking about the actual prototype itself, blue chip, and then UCI. I'll get into further detail about that later, but they're both used and explained in this project. And then we're going to get the results of this. We will see how blue chip and UCI fared when tested. So here's the background. So here's a few questions first before we get into it. The first question is, do you think malicious hardware is more dangerous than malicious software? Now, contrary to what some of you might think, malicious hardware is actually more dangerous than malicious software. And there are actually two reasons for this, two key properties for this. The first one is hardware is a more persistent attack vector. Now, what I mean by that is if you find a software vulnerability in a computer or on a phone, you can easily just patch it by sending an update or something along those lines. However, with a hardware vulnerability, it requires physically replacing / fixing that. You can't just put in an update. You have to actually take out that circuit and then put in a new one, or else it's never going to be fixed. The other key property of why malicious hardware is more dangerous than malicious software is that hardware is the lowest layer in the computer system. Now, what I mean by this is software runs above hardware. So if there is a malicious circuit, aka malicious hardware, then it is hypothetically able to control the software running above, giving the attacker the ability to avoid any software-based defenses, seeing as how software-based defenses are only guarding against malicious software. Now the next question here is, what makes malicious hardware so dangerous? Now, the reason that people think malicious hardware is dangerous, not think, but know malicious hardware is dangerous, is because malicious hardware provides a foothold for subsequent system level attacks. For example, during a design time of this computer, attackers can insert a malicious event that only triggers when an attacker introduces a sequence of bytes, and then the attacker would get a quote-unquote foothold in the system and then can take control of the system as they would want to. Now, how does blue chip fit into this? Blue chip is used to combat the problems here. So basically, during the design phase, when someone might insert like a malicious hardware, blue chip would flag that malicious hardware, aka any suspicious / unused circuitry, and then deactivate that. However, there are a few scenarios when suspicious circuitry is part of the legitimate circuit. So, blue chip inserts circuitry to raise exceptions whenever a suspicious circuit is activated. And then blue chip has its own software that is responsible for emulating hardware instructions that allows the system to continue in execution even if the legitimate circuit is taken out. I'll go into further detail on this later in this presentation. So, important. Why do we care so much about this? Why is this so big? So, as modern hardware systems get more complex, they are becoming increasingly vulnerable. And what I mean by increasingly vulnerable, it is easier to hide stuff, insert malicious circuitry undetected, and create a quote-unquote hardware Trojan horse. Because as things become more complex, the harder it is to see details. And then for attackers, this introduces somewhat of a low risk and high reward attack. Now, the reason that there is so little risk is that there is little risk of punishment to the attackers because it is very complex, and there are, as noted earlier, with the greater complexity, it becomes harder to distinguish unintentional bugs between intentional bugs. So someone might think that a bug is unintentional, but in reality it's really there on purpose, while vice versa, someone might think a bug is there on purpose to give an attacker something there, but it's just someone who unintentionally put it there. So it's kind of difficult to prove malice. So then the attacker has low risk that they might be found or they might be prosecuted for this, but they get a high reward. They have an ability to get access to the system, gain full control of the system. So now the threat model of this whole thing. There are going to be two scenarios analyzed in this paper. The first scenario is an internal threat, for example, a disgruntled employee inserting malicious circuits. So what an employee could do is, before the final design validation, they can quietly insert a malicious circuit into it and hope those changes are unnoticed. And then those small changes that they put in are sufficient enough to create a powerful malicious circuit design for bootstrapping a larger system level attack, or like a foothold. And then these persist even after the malicious software is removed, because as we mentioned earlier, if you remember, when software runs under hardware, hardware runs under software, so malicious hardware can take control of software. So even if you get rid of the software, the malicious hardware is there until you physically remove it. The second threat to be analyzed here is external. So an attacker can create a new IP or modify an IP block to add a malicious circuit. An IP block in this scenario is an intellectual property block. So typically what happens when circuits are being made is a lot of these like engineers, they take stuff from the internet to try and mesh things together to make it easier to make and more efficient. However, sometimes we can't trust these IP blocks. So what attackers do is they distribute and license IPs to the design engineers in hopes that what an actual term is SoC creator, or a system on chip creator, will incorporate it and then include it in that fabricated chip. So now that if it's included in the fabricated chip, the designer won't know that at first that there's a malicious circuit in there, and only through testing will they figure that out. But as we will go into further detail, sometimes these tests cannot find out or will not find those malicious circuits. And one thing to note here, an assumption for the internal threat, is that it's assumed only a few portions of the design team are acting maliciously. We also assume that the individuals who actually do the final verification and validation are not compromised and aren't working with the original malicious employees. So now I'll be talking about Blue Chip's approach. So here's a brief overview of what we've been talking about so far. So as you can see in part A, a design engineer would design a circuit, take stuff from everywhere, and then for their job. And then in part B, while the design engineer is taking stuff and making a circuit, sometimes internally someone might purposely put in a malicious circuit, or externally, as they are taking stuff from the outside world to put in their circuit, they might accidentally take something that an attacker put out there. And then all of a sudden they have a malicious circuit inside their circuit. So in part C, that's where you have these test cases, you have design verification and final validation. That's where these tests come into effect, whether they start looking and seeing if there are any suspicious circuits there. And sometimes, however, that original portion doesn't work. So what happens is in part D, when they're actually running it, around those final tests and stuff, that's where Blue Chip comes into effect, so they can pass these malicious circuits and make sure that they don't trigger and take control of the system. So now we'll be talking about the Blue Chip's design. First, we'll be talking about the hardware. So there are three general requirements to apply Blue Chip to hardware. The first one is there must be a hardware exception mechanism for passing control to the software. The second one is Blue Chip must prevent this modified hardware state from committing immediately when the hardware triggers a Blue Chip exception. And the third one is, to enable recovery, this hardware must provide software access to the hardware state. And when I mean hardware state, it could be like processor register values and other architecturally visible states. So now we'll be talking about the software side of it. So the goal of the software is to recover these hardware exceptions. As if you can recall on the last slide, one of the requirements was that these hardware exceptions must be able to pass it on to the software side. And this is the software side. So what the software is technically responsible for is recovering these hardware exceptions and providing a mechanism for system forward progress. Because sometimes there's unusual design challenges for the software, and some features of the processor may now be unavailable as they were taken out because the system thought that they were unsafe or illegitimate. And in order to handle these cases and stuff like this, that's where emulation comes into play. So emulation here entails that for each instruction, the blue chip software reads that instruction from memory, decodes that instruction, it calculates the effects of the instruction, and then commits the register and memory changes itself. So what's happening here is blue chip is doing the hardware's job for it, but making sure that the hardware doesn't do it itself so that an attack isn't triggered. Now, there is a problem with this because sometimes when this happens, sometimes the emulation routines depend on the removed hardware, aka the suspicious/illegitimate hardware. So this would cause unrecoverable recursive blue chip exceptions. So for example, one attack would trigger a specific value observed. Well, one attack could be if a specific value is being observed stored in the memory. So blue chip identifies and removes these attack circuits obviously because it's a malicious circuit, and it triggers an exception so that whenever the software attempts to store an attack value, that blue chip steps in. However, this leads to a store emulation instruction simply reissuing the same address and value instruction over and over again, creating an unrecoverable recursive exception. So, to avoid this, blue chip emulates around the faulting instructions by producing a semantically equivalent result while avoiding blue chip emulation states. So, for example, as you can see here, this is how they would do it. So, for an ALU operation like OR, they could do something that's similar to this by just doing a bunch of XORs, NANDs, and then they would store it. So basically what's happening here is it's basically the same instruction with a few extra steps, but since the OR isn't technically occurring, the malicious circuit does not see that as a trigger and just ignores what's going on, and the malicious circuit is never triggered, and we don't have any recursive problems happening anymore. Now another question. How do we detect suspicious circuits? So the answer to that would be developing an algorithm that identifies these malicious circuits. It should be difficult for an attacker to avoid, and the algorithm should automatically detect this malicious code without the defender having to make a new set of design verification tests. So typically what happens is the design tests for hardware are extensive, and these test cases usually have a set of inputs and verifies that the hardware circuit outputs what they expect. So these design verification tests would help the defenders detect attack targets, because if there is an attack circuit, hypothetically, those attack circuits would contaminate the outputs for a test case. However, recently attacks have been designed to not trigger during these routines or like routine tests. These evasive attack techniques works by making sure the attack circuit only activates when a specific sequence of events/data value is being observed. One possible approach that they take now is the strawman approach, aka code coverage. So what happens here is they basically use code or use these tests to cover each line of code to make sure that they are executed, and then they would highlight these uncovered lines of codes that potentially contain malicious circuits. However, as you can see here, attackers can easily craft circuits that are covered by testing but don't trigger an attack. Here in this example, it shows a multiplexer circuit that is covered fully without outputting the attack values. So every line is technically used, and so no lines will be highlighted for being suspicious since they are not used. So how do you work around this? This paper proposes unused circuit identification or UCI algorithm. So how does UCI work? Like, how is it different from like code coverage or anything? To identify these malicious circuits, this algorithm performs two steps. The first step is UCI creates a data flow graph for the circuit. In the graph, nodes are signal/state elements. Edges indicate data flow between nodes, allowing UCI to generate a list of all the data flow pairs or data flows from the source signal to the sink signal. This includes both direct and indirect dependencies. And then, in the second portion, UCI simulates this HDL source code using design verification tests to find sets of data flow pairs where the intermediate logic does not affect the data that flows between the source and SIG signals. Once the simulation completes, UCI is left with a set of remaining data flow pairs where the logic in between the pairs does not affect the signal value between source and sink. The resulting output after this UCI simulation identifies the malicious circuit without identifying any additional signals, as the circuit systemically identifies circuits that avoids affecting outputs during testing. How does Blue Chip use UCI? Here is a picture for you all. Basically what happens is UCI outputs a data flow pair. The source and sink elements can be connected directly by a wire containing delayed number of registers, effectively short-circuiting the signals with the delay line. Blue Chip implements short circuits by preventing a source-to-source transformation on the design's HDL source code. As you can see in part A, UCI identifies an attack. After UCI generates a set of data flow pairs, the pairs are fed into the Blue Chip system. Blue Chip then takes these pairs as inputs and replaces suspicious circuits by modifying the HDL code. As you can see in part B, this is an example of what happened if Blue Chip transforms an HDL source code to remove the attack. But what happens if multiple data flow pairs share the same SIG signal? The HDL transformation algorithm must also be able to handle these multiple data flow pairs that share the same sink signal but have different sources. This could cause problems for Blue Chip as it is unclear which source signal to short circuit to the original signal. So the solution for this is to pick one pair for the sink signal assignment, but to add exception generation logic for all pairs that share the same sink element, meaning all violations are detected, but sink may be shorted with source that caused exception. This is safe because Blue Chip asserts exceptions immediately when detecting inconsistencies. Blue Chip checks all those data flow pairs for inconsistencies and then leverages hardware recovery mechanisms to prevent the persistence of untrusted state modifications. So, malicious hardware footholds. What is Blue Chip looking to defend against? The answer to this question is footholds. Now, you might be wondering, what is a foothold? So, prior work has been done on developing hardware attacks that focus on adding minimal additional logic gates as a starting point for a system-level attack. So basically, these minimal additional logic gates sort of crack the door open and give the attacker an opportunity to open this door further and gain more control of what they're trying to get. So there are three types of footholds that Blue Chip looks to deal with. The first foothold that Blue Chip is wanting to deal with is the supervisor transition foothold. This foothold provides a hardware mechanism that allows unprivileged programs to transition into a supervisor mode, bypassing usual hardware-enforced protections. Basically, for example, someone might only have read and view permissions, but now they have read, write, and view permissions. So this malicious hardware is usually triggered when a sequence of instructions is observed being executed by the processor. And in this scenario, this particular sequence is hard-coded. The next foothold is the memory redirection foothold. Now, what this foothold does is provide hardware support for unprivileged malicious software by allowing an attacker to access arbitrary virtual memory locations. This foothold is triggered by using a sequence of bytes as the trigger. When the foothold observes these store instructions within a particular sequence of bytes, it interprets that as the trigger and then the subsequent bytes as the redirection address. the malicious logic would then record the address of the block and redirection address. And then when the address is next loaded from memory, the malicious hardware substitutes the redirection address as the address to be loaded and then asserts the supervisor bit past the memory management unit. Basically, the net effect of this process is providing full access to any arbitrary virtual memory location and bypassing any MMU, aka memory management unit, protections enforced in the processor. This gives flexibility for the attackers, as attackers can trigger their circuit with only data values through a number of techniques. And then the third and final foothold that Blue Chip looks to deal with is shadow mode. A shadow mode foothold allows an attacker to inject and execute arbitrary code. And this typically works by the circuits monitoring data values as they pass between cache and pipeline and installs invisible firmware in the processor when a specific value triggers an attack. When firmware runs, it has full processor privileges, can gain full control at any time, and remains hidden from software on the system. Foothold reserves blocks in the instruction and data caches for storing injected instructions and data. This foothold is usually triggered by a sequence of bytes, and shadow mode footholds interprets these bytes as commands and instructions. So now we will be talking about the Blue Chip prototype. So, as mentioned earlier, there is a hardware and a software side to Blue Chip. For the hardware side, the hardware implementation was based on a Leon 3 processor design and implements the Spark V8 instruction set. For the software side, it was a Spark port of a Linux 2.6.21.1 kernel, and there was a full Slackware distribution installed on the system. So next, how did Blue Chip fare? Before we get on to the actual results, we should go over the setup of the testing environment / simulation. So there were 3 sets of verification tests. The first set was basic test suite included with the Leon 3 distribution, or the Geisler test suite. The second one was the Spark certification test cases from Spark International. And the third one was 5 additional test cases to test portions of the instruction set specification that were uncovered by the basic Leon 3 and Spark certification tests, or the first 2 test sets. And there were also 3 workloads that were used here to stress different parts of the system. The first workload, wget, fetches an HTML document from the web and represents a network-bound load. The second workload, make, was compiled portions of the NTP-date application and stressed the interaction between kernel and user nodes. The third workload, djpeg, decompressed a 1 megabyte JPEG image as representative of a compute-bound workload. And now for the results. So there were 2 goals here that Blue Chip looked to do when defending against malicious hardware. The first goal was prevent. It looked to prevent attacks from influencing the state of the system. The second goal was recover. It looked to help the system recover, allowing non-malicious programs to keep making progress even after an attack was attempted. As you can see from these results, Blue Chip was able to prevent 3 of the 3 attacks: privilege escalation, memory redirection, and shadow mode. Unfortunately, Blue Chip was only able to recover 2 out of the 3 attacks, not being able to recover against the memory redirection attack. Now, the reason it was not able to recover for a memory redirection attack was due to the fact that Leon 3's built-in pipeline recovery mechanism was insufficient to clear the attack's internal state. Thus, the Blue Chip hardware repeatedly trapped the software. It blocked forward progress, not meaning it was not able to recover, but it prevented the attack from happening. So, in conclusion, Blue Chip worked to neutralize malicious hardware. Blue Chip also was successful, as the experiments we just talked about showed, and it showed that it is cost-effective and practical to address malicious hardware problems, and that we should continue research into this, as this is a big problem that is, as of now, still not fully solved. And here are the citations that we have. And thank you for listening to this presentation.